Okay, let's start. So welcome to today's central exercise session, the last central exercise session of this semester. We'll be discussing sheet number 12 today. As usual, we'll be happy to take your questions on our chat channel. The chat is available here at chat.tum.de. And please use this channel here, MA9711-CE, to ask your questions. We'll monitor that chat channel, and as usual, the chat will be moderated by Lisri Fernandez.
Hello, everybody, and welcome to the last session of the central exercises. I just wanted to remark that all the questions that they are not related to sheet 12, they are going to be asked by at the end of the session.
Okay, thank you. Let's start with sheet 12 then, and if there's any other questions, we'll be happy to take those at the end, as Sri just said. So, we start with C12.1, which is on L'Hopital's rule. So the task here is to compute a few limits using L'Hopital's rule and to check whether L'Hopital's rule may actually be used. The first one is a pretty standard problem here. We have x tending to infinity, and we want the limit over ln of x to the power of 6 plus 1 over ln of x to the power of 3. And as you know, with x tending to infinity, of course, x to the power of 6 tends to infinity, and the ln of something that tends to infinity also tends to infinity. So the numerator tends to infinity here. And the same is true for the denominator. X to the power of 3 tends to infinity, so the ln of x to the power of 3 also tends to infinity. That means we have a situation, a limit of the form infinity over infinity. And that means we can try to apply L'Hopital's rule if the functions involved are differentiable, and those functions obviously are differentiable. So make a quick note here to indicate that I'm going to use L'Hopital's rule. And what we have to do is we just have to differentiate the numerator and the denominator separately. And then the limit over those derivatives should be the same as the original limit if those new limits exist. And that's the one other thing that you have to check, whether those new limits actually exist. So the derivative of the ln function is 1 over the argument. So what we get for the numerator is 1 over x to the power of 6 plus 1. And then, using chain rule, we also have to multiply that with the derivative of the argument. So that derivative is 6x to the power of 5. And the same basically applies to the denominator. Here we have 1 over the power of x, 1 over x to the power of 3, sorry. And again, we apply chain rule, so we need to multiply that with the derivative of x to the power of 3, and that is 3x to the power of 2. Now let's try to simplify that a little. First, we write all factors on just one fraction as either numerator or denominator of one fraction. So here we have this x to the power of 3. That goes into the numerator. Then we have 6x to the power of 5. This here goes into the denominator, so we have x to the power of 6 plus 1 here, and we're left with this one, which is also in the denominator, 3x squared. Now let's simplify a little more. What do we get here? Let's see. So x to the power of 2 cancels out. Let's say with this one here, that leaves us with 1x. And 6 and 3, we can also cancel a factor of 3 out here. So that leaves us with 2x times x to the power of 5, which is 2x to the power of 6. And for the numerator, we get x to the power of 6. Sorry, for the denominator, we get x to the power of 6 plus 1. So this is the limit that we need to compute. And that is, of course, just a standard limit. We can, for example, divide everything by the highest power of x, which is x to the power of 6. And we get 2 over 1 plus 1 over x to the power of 6. And then this here tends to 0. So the denominator tends to 1. And of course, the numerator is just 2. That is not dependent on x anymore. So that limit is 2. And what is important is to remark that obviously that limit exists. So after this L'Hopital step here, the new limits actually exist. So that justifies the application of L'Hopital's rule. So the limit exists, and that means L'Hopital's rule can actually be applied. Right? If we had gotten something like the limit is infinity or something like that, then that would mean the limit does not exist. And thus, the application of L'Hopital's rule was not possible to start with. So we'd have to find some other way to compute that limit in such a case. Okay, are there any questions about that first subproblem?
Yeah, indeed, there was a question that you just answered that it says if the new limit after applying L'Hopital rules does not exist, do we have to try another approach to get the limit of the problem?
Yes, correct. So L'Hopital's rule is only applicable if the new limit actually exists. And that also means it cannot be infinity or minus infinity. It has to be a finite real number.
When are we allowed to use L'Hopital's rules? In the definition we wrote, if limit fx is equal to limit gx, but in the example B, afterwards we have limit fx equal to minus infinity and gx plus infinity, but still we use L'Hopital's rule.
Yes, I get to B in just a second. I'll explain how to use L'Hopital's rule later.
Can we use another color in exam? Okay, sorry, I didn't. It is sufficient to write the case type zero divided with 0 before using L'Hopital in the exam?
So you should somehow justify using L'Hopital's rule, and of course you should also indicate that you are using L'Hopital's rule. I usually do something like this, but feel free to write something else that's understandable. And you should somehow justify that by first giving an indication that you have either the type infinity divided by infinity or 0 divided by 0. And of course, you should also make a statement somewhere that the limit actually exists, and thus the application of L'Hopital's rule was justified. So those two things, one statement like this and something like this, that should be present in the exam, please.
Are we allowed to use L'Hopital's rules for sequences or just for function limits?
That depends a little on how the sequence is defined and whether that makes sense. So for some sequences, it would be possible to kind of extend those to a continuous and differentiable function by just applying the same definition to all numbers. And then, of course, you can use L'Hopital's rule for that. For some sequences, that might not be possible or might not make sense. For example, if you include something like n factorial in the sequence definition, we haven't talked about how to generalize an expression like that to the real numbers. So you can't do that.
Okay, and there is a question related to exercise 12.7, so I will collect it to the end, and there are no more questions.
Great, thanks. So then let's have a look at B. And as you've remarked correctly, B is of a different form. So in this case, we want to find the limit of x times ln x as x approaches 0 from above. And as you can see, that limit is basically of the type we have x which approaches 0, and we have the ln x. You hopefully remember how the ln looks like. So basically, the ln function is something like this here, right? So as x tends to 0, the ln tends to minus infinity. Right? So this here tends to minus infinity. And that means we have something of the type 0 times minus infinity, which is not one of the types that we can use for L'Hopital's rule. We either have to have 0 divided by 0 or infinity divided by infinity. However, there's a number of standard tricks that you can apply to try and reformulate these limits into an appropriate form. And one such trick would be to, instead of multiply by a factor, we can divide by 1 over that factor, right? So instead of multiplying by x, we can just take that ln and divide by 1 over x. That's the same thing. And now that means, well, if x goes to infinity, x goes to 0, sorry, then 1 over x goes to infinity. The ln goes to minus infinity. So again, we have something of the form infinity over infinity. The sign doesn't really matter here. Yeah, we could factor that out if you wanted to. So now we can try to apply L'Hopital's rule. Both functions are differentiable. So we can easily apply L'Hopital's rule and see if the resulting limit will actually exist. Now, if we do that, what happens is we get the derivative of the ln, that is 1 over x, and the derivative of 1 over x is minus 1 over x squared. So let's simplify this a little to get the result. That means this 1 over x, that is 1x in the denominator. And here we have 1 over x squared, so that's in effect an x squared here in the numerator. And we also have a minus sign here. So that's minus x squared divided by x. Well, and that means what we actually have here is the limit as x tends to 0 of minus x. And of course, that is just 0, so that limit does exist. Let's make a quick note about that. Limit exists. So L'Hopital's rule applies. And that means that computation was actually correct, and we were able to compute that limit as having a value of 0. So, questions about this one?
Yeah, so there is a question I didn't really follow, and I was just asking to rephrase it. Like, does it matter if we put it in the denominator or x in the, then I guess in the denominator or in the numerator? I do not really follow.
So I can try to make an educated guess. You could also have done something like x over 1 over ln x as another way of reformulating that expression, x times ln x. And that would mean you have a numerator that tends to 0, and you have a denominator that tends to, well, ln x tends to minus infinity, so that also tends to 0. And that gives you an expression of the form 0 divided by 0. So again, you can try to apply L'Hopital's rule. Of course, if you try to differentiate that expression, you will get something like 1 over ln squared times something. And that doesn't look as nice as the result that I got here. So I would prefer this approach. And I'm actually not sure if that leads to anything useful. Yeah, but you can do both reformulations, and you should use the one that is easier once you do the derivatives.
That was indeed the question. And now, what other tricks are there to do this exercise?
What are these, sorry, the tricks?
Tricks?
That was one of the tricks. I basically collected all of the tricks that you should be aware of in the lecture videos. There's a video on examples about L'Hopital's rule, and I'm going through basically all the typical reformulations there.
Now there is an interesting question. Would it be possible to say that 0 times minus infinity equals 0 because something multiplied with 0 is 0?
That's not necessarily true in the limit. So consider something like the limit of, let's say, 1 over x. Let's say x tends to infinity, so 1 over x surely tends to 0. And then let's multiply that by x to the power of 43, which tends to infinity. And I hope you'll all agree that this is actually the same thing as x to the power of 42, which tends to infinity. So that is not 0. It's very far away from 0. So basically what I'm trying to say is in a situation like that, anything can happen. Yeah. Another example, much easier. Consider 1 over x times 2x. That limit is just 2. And of course, I could use any factor here, yeah? So I'll be able to produce any value you want and write that as an expression that looks like 0 times infinity. So that's not so easy.
So if both functions tend to infinity, the sign never matters because we always are able to take it outside?
Yes, right. If both functions tend to plus or minus infinity, we can always take the sign outside of that. Of course, we have to respect the sign when we actually compute the limit, but we can apply L'Hopital's rule in both situations.
No more questions by the time being.
Good, so let's have a look at C. So in C, we again have a limit. Let's write that down first. We have a limit of, where is it? Sorry. Here. Of sine pi x times the ln of the absolute value of x minus 1 as x tends to 1. So what we have here, the sine of pi x, basically make a quick sketch of how the sine looks like. Sine function that basically looks like this, and here's pi, here's 0, here's 2 pi. So the sine of pi x as x goes to 1 goes to the sine of pi, and that goes to 0. So that means this factor will go to 0. The absolute value of x minus 1 will go to 0 from above. So this ln will tend to minus infinity. So again, we have something of the form 0 times minus infinity. And again, we have to reformulate that to get an expression that we can use for L'Hopital's rule. And in this case, again, I'd like to have the ln on top, because the derivative will be much easier if I can differentiate the ln and not 1 over the ln. So my reformulation looks like this. I have the ln here, and then instead of multiplying by the sign, I divide by 1 over the sign. So that'll look like this here. And now, of course, we have an expression where the numerator goes to minus infinity. This here goes to, depending on whether we approach one from the left or from the right, this will go to plus or minus infinity. So in either case, we have an expression like infinity over infinity. And that's what we wanted here. The one other problem here is that we have this absolute value that is not nice in terms of differentiation. So to treat that formally, we'll have to resort to one-sided limits. And then we're able to remove that absolute value here, or reformulate the absolute value. And that will enable us to actually take the derivative. We'll only be talking about one-sided derivatives formally here, but that doesn't really make a difference in that case. So what we'll do is we'll first try to compute the limit as x approaches 1 from above. So if that is the case, then x minus 1 is positive, and that means the absolute value of x minus 1 is the same as x minus 1. So in that case, the expression that we need to work with is the ln of x minus 1 divided by 1 over the sine of px. And now we can apply L'Hopital's rule. And if we do that, this time we get an expression that looks a little more complicated. So the ln, that's the easy part. The ln is just 1 over x minus 1. That sign expression here is a little more complicated. We first differentiate the expression 1 over something, the outer function, that is 1 over something squared and the minus. So we have minus 1 over sine squared pi x. Then we multiply with the derivative of the inner function, which is sine pi x. The derivative of that function is cosine of pi x. And again, there's an inner function to that. So we have to multiply with the derivative of that one as well. And the derivative of pi x is just pi. So that's the derivative of the denominator here. Now again, let's simplify things a little to see if that already helps. So what do we get here? This 1 over the sine squared is the same as putting the sine squared here in the numerator. So we have sine squared pi x. This x minus 1 goes into the denominator, and all the other factors are also in the denominator. So we have cosine pi x, we have pi, and don't forget about that minus sign here. Just add that here. Okay, now if we try to substitute 1 into that expression, then of course that sign still goes to 0. This here also goes to 0. And the cosine of pi x, let's make a quick sketch of the cosine as well. So it's basically a translated version of the sine that looks like this here. Here's pi. So the cosine of pi x is minus 1. And that means the denominator as a whole tends to 0. So now we have something like 0 over 0. And again, we can try to apply L'Hopital's rule to that one. So we still don't know whether the first application was actually justified because we don't know whether that limit exists. We can try to just apply L'Hopital's rule once again and see what happens. So let's do that. Now differentiating that sine squared, that yields minus 2 sine pi x. Again, we have to apply chain rule. We have to multiply by the derivative of the inner function, which is cosine pi x. And once again, we have to differentiate pi x, multiply by that derivative, that is pi. And for the denominator, let's see, we have a product of two functions plus that constant of pi here. So you can just take the pi outside. Do not have to worry about that one. Then we start by differentiating this expression here. So the derivative of x minus 1, that is just 1, times that cosine function. And then we add this times the derivative of the cosine function, so plus x minus 1 times, and the derivative of the cosine is the negative sign. So we have sine pi x, and let's change that here to a minus. Maybe let's mark that in red. So this here becomes a minus because of the derivative of the cosine. And once again, if we differentiate cosine of pi x, we have to take care of the inner function, which is pi x, and the derivative of that one is pi. Okay, so that yields the next expression we have to take care of. So let's see if that actually helped. Now, in that case, we have that sine of pi x that still tends to 0. We have that cosine that still tends to minus 1. All the rest are constants. So the whole numerator tends to 0. For the denominator, we get a minus 1 here. We get this tends to 0. This also tends to 0. So basically we have pi times minus 1. So that tends to minus pi. And now we still have that minus sign over here, right? Don't forget about that one. So we can just move that into the denominator, and then instead of minus pi, we get plus pi. But it doesn't really matter for the result, of course. So what you get as a result is 0 divided by pi, which is, of course, 0. So in this case, we had to apply L'Hopital's rule more than once, and the derivatives were not that easy anymore, but in the end, it all worked out. So both applications of L'Hopital's rule were actually justified. So L'Hopital's rule could be applied because that limit exists in the end. Now that was, of course, only one side of that limit. We basically have to do the same thing again for the limit of x tending to 1 from below. In that case, x minus 1 is negative, so the absolute value of x minus 1 is 1 minus x. And that means we can just do that reformulation that we had before. We can do that again. So in this case, we have the ln of 1 minus x divided by 1 over the sine of pi x. And then basically the same arguments work. Yeah, we can again apply L'Hopital's rule because we have something that tends to infinity here and to infinity here, or rather to minus infinity. So we can again apply L'Hopital's rule. We get again an expression that is similar to the one before, plus minus. And again, we apply L'Hopital's rule once more. In the end, the result is basically the same up to a sign somewhere. So what we get is the limit of 0 over minus pi, or 0. I'm not going to bother you with the details. That's a nice exercise you can do for yourself. So what that means is both one-sided limits exist. And that, in effect, also means that the original limit exists. So both one-sided limits exist, and they have the same value. And that means the limit that we started with, x tends to 1, of, how do you write that here? Sine first. Sine of pi x times the ln of the absolute value of x minus 1. That exists and has also that value, which is 0. So we finally succeeded in computing the limit that we started with. Questions about this one?
Okay, so there is a question that it says, would it also be possible to solve 12.1b by putting the function into the exponential function? And I do not really see how, so I'm not sure whether you understand it better.
Putting that into the exponential function, don't see how that would help, actually.
I mean, the only thing I could think of is like x times logarithm of x, like we could write it as logarithm of the exponential of x times logarithm of x, but I don't really see how it works. I mean, how
so
it
you could get something like this here, right? Which is x to the power of x, but then what? How do you get that limit? So you can try that, of course. It's always worth a try if you don't have an easier way, but I don't think it helps in this situation. At least I don't see how.
Yeah, me neither. Now there is a question that it is, are we supposed to apply L'Hopital's rule until we find a limit? Well, as far as you can apply it, right?
Yes, if that's possible, yes, of course. I mean, if you have not found a limit after one application of L'Hopital's rule, right, where was that? Right here. So here we applied that L'Hopital's rule once. We got this expression here, and we cannot determine that limit right away, because we still have a situation that is of the form 0 over 0, and I don't see a clever way of determining that limit without using L'Hopital's rule, at least not an easier way than that. So you can just try to apply it once again, and you do that as often as necessary until you either arrive at something that you can easily compute, or until you see that actually the limit doesn't exist and all those L'Hopital's rules were not justifiable.
Okay, so I have a question regarding the infinity over infinity case. You said we can always take the minus out, but we have to consider it later on when we compute the limit. Didn't we reconsider it in the example because the limit was 0? If it were not 0, should we multiply the limit by -1 then?
So for the application of L'Hopital's rule, for the applicability of L'Hopital's rule, it doesn't really matter whether you have plus or minus infinity over plus or minus infinity. That's what I meant. You can apply it in either case. Of course, for the limit itself, it will make a difference, right? So you have to have a look at the signs then. In this case, there's no difference because we get 0 anyway. So whether we get plus 0 or minus 0 doesn't matter. Otherwise, of course, we would have to respect the sign that turns out in the end. Right? And if a one-sided limit is involved here and something goes to 0, then of course you'd also have to have a look at whether that approaches 0 from above or from below. That might also affect the sign. Yeah? If it goes to 0 from above, then that's a positive sign. If it goes to 0 from below, that will be a negative sign. That doesn't matter here, but it might matter.
Would it be allowed to skip the computations in the limit from below in the exam?
Oh, you might like add it here. No, of course not. No, so I would expect you to write this out.
Ah, okay.
Then I would probably not make it that easy for you.
When exactly do I know I made it to the end performing L'Hopital rule?
Whenever you get a limit that you can compute.
Yeah. Could you please explain how the absolute value was transformed to 1 minus x again?
Well, basically what I did here is if I said if this here is negative, it's a negative number like -7. What is the absolute limit of -7? The absolute value of -7? That is, of course, +7. Or you could write that as, well, let's write that down actually. So the absolute value of -7, you could write that as -7, and that's +7, right? And that's exactly what we're doing here. We would say this here is negative. So the absolute value of this expression is minus that expression, and that is simply 1 minus x. That is what is happening here.
Now, can we apply L'Hopital's rule with sin x divided by cosine of x?
For x tending to what?
Yeah, I think really doesn't matter, right? Because when the sine gets 0, the cosine won't get 0. And
yes, exactly.
I think there's no case we can really get.
I don't see a case where you could actually apply this because they will not be 0 at the same time and neither tends to infinity.
What happens if we end up with an expression like 4 divided by 0 and L'Hopital's rule cannot be applied anymore? Does that mean that the original limit does not exist or that we cannot use L'Hopital's and hence have to use another method?
Yeah, the second one. So that would mean you cannot use L'Hopital's method. That rule is not applicable. And that means we don't know anything about the original limit. It does not mean that the limit doesn't exist. It might not exist, but we don't know. L'Hopital's rule just doesn't work in that situation, so you'll have to find some other way to compute that limit.
What would happen if the one-sided limits do not have the same value? Does this apply that the L'Hopital rule is not possible or that there is no limit for the function?
So if one-sided limits do not have the same value, both exist but don't have the same value, then still L'Hopital's rule was applicable. So in this specific case, for the one-sided limits, we could apply L'Hopital's rule. It worked fine. So we got limits here. But if they don't agree, then that means the original limit just doesn't exist. So in this case, we do get a result, which would be the limit doesn't exist.
No more limits. Sorry, no more questions.
Wonderful. So let's move on to the next problem, which is not about limits. So C12.2, that is about Taylor. So in this case, we have a function which is given as f of x equals x ln x squared, defined from 0 to infinity. And we want to determine the Taylor polynomial T2 of f at 1. Right, so this here means the Taylor polynomial of degree 2. That's the degree of that polynomial. And this here is the point in consideration. So we want to have the Taylor polynomial around the point x equals 1. Okay, and by the way, if there's no number here, that would mean the Taylor series. So basically substitute infinity if there's nothing there. So let's have a look at how to do that. For the Taylor polynomial, the general formula for Tn f of x around some point, we call it x0 usually. That would be given by the sum over k from 0 to n, so here's a degree, over the kth derivative at x0, that is where the x0 enters, divided by k factorial times x minus x0 to the power of k. And once again, x0 enters here and here. Okay, that's a general formula, and for a series, you just let that sum run to infinity. So what we need to do to get this T2 of f is to compute the first two derivatives, and of course the zeroth derivative, which is just the function value. So we start with that. So the zeroth derivative of x is formally just the function itself, which is x ln x squared. And we need the value at the point 1. So if 0f at 1 is, well, it's just 1 times ln 1 squared. ln 1 is 0, so we get 0. For the first order derivative, let's see, take the derivative of that function here. We get 2x ln x times, and now we have differentiated the outer function, which is that square function here. We now have to multiply with the derivative of the inner function, x times ln x. And that's a product of two functions, so we apply product rule. We first differentiate that x, so that's 1 times ln x, plus, and then we keep the x and differentiate the ln, that is 1 over x. So this is that derivative here. Again, we're interested in, let's simplify that first. We need to take another derivative after all. So what do we get? We get 2x ln x squared plus x, this here x over x is simply 1, so that's plus 2x ln x. And then we can compute f1 at the point 1. That would be 2 times 1 times ln 1 squared plus 2 times 1 times ln 1. Ln 1 is 0, so what we get is 0 plus 0, which again is 0. So the first order derivative is also 0 at the point 1. And now let's compute the second order derivative. Let's see. So we need to take the derivative of this expression here. This is obviously a product, and well, it has 2x in both cases. So we can just factor that out here to make things a little easier, hopefully. So that's 2x times ln x squared plus ln x. And then we apply product rule to that expression. Differentiating that here simply yields a 2. So we have 2 ln x squared plus ln x. Plus, and then we have 2x times the derivative of that expression here. Now ln x squared, that yields 2 ln x times, and then we have to multiply this with the derivative of the inner function ln x, which is 1 over x, plus, and the derivative of ln x here is just 1 over x again. So what we get is 2 ln x squared plus ln x. Oops, sorry. Like this. Plus, and here we just take the x inside to get rid of those 1 over x expressions here. So that's plus 2 ln x plus 1. And again, what we're really interested in is f2 of 1. So we need to substitute 1 for x, and we get 2 times ln 1 squared plus ln 1 plus 2 times 2 ln 1 plus 1. And you can see almost everything is 0 here. The only factor that remains is this plus 1 here times 2. So what we get is 2. Finally, a non-zero derivative. Well, that yields the Taylor polynomial. Again, let's have a look at the general form here. Let me copy that. So that's the general formula. That means RT2 is given by, well, we start with F0 add 1 times 1. Then we add F1 add 1 over 1 factorial, that's just 1, times x minus 1. And then we have F2 add 1 over 2 factorial times x minus 1 squared. So using the values that we just computed, this factor is 0, this factor is 0, that's the only factor that remains. This was 2, right here. So we get 2 over 2 factorial, which is 1. So all that remains is x minus 1 squared. We get that simple approximation here through this Taylor polynomial of order 2. So that completes 12.2. Any questions in this one?
Yeah, it says, would it be a mistake not to simplify the derivative and just input x equal to 1 as soon as we have the derivative?
That's fine. You don't have to do the simplifications. It might be useful if you have to take more derivatives, right? Because then the basis of taking these derivatives is easier. But you don't have to do that, of course.
Okay, there is somebody writing something, but so far there are no more questions. Well, how could now the Taylor series look like, and how could we know and how could we now investigate whether it converges or diverges in its domain?
So we'd first have to have the actual Taylor series, of course. Up to this point, we only have the Taylor polynomial of degree 2. And the Taylor series would require to have an expression for the general derivative. So we'd have to have a formula for that. I haven't really looked into that, but I guess that might not be so easy. I mean, as you can see, those derivatives didn't look very nice at the end, and they tend to get more complicated with each step. So I don't immediately see an easy way to have a general formula for the derivatives. And you would need something like that to come up with the Taylor series.
So another question says, what is the difference between the Taylor series and polynomial?
Well, very simple. The Taylor polynomial is just a polynomial of a given degree, n in this case, so there's some n's at n. The Taylor series would be pretty much the same thing. Let's copy that so I can just make the necessary adjustments. So for the series, the notation would be without this n, that would be the series, and I will also remove that n here, and instead put an infinity there. That would be the Taylor series. And of course, that would not answer the question of whether that converges at all anywhere but at x0. And it does not answer the question how to get that. You have to have some idea of how that general, derivative here looks like. Did I forget those? Yeah, above. Let's add those as well. Sorry about that. Yeah, so that's the series.
Okay, then there is another question. It says, should we write out x minus 1 squared, or is it sufficient to leave it as such in the exam, especially if there are more polynomials?
So in that case, I would advise to leave it in that way, because we wanted the Taylor polynomial around 1, and that involves factors of that form here, x minus 1 to the power of something. So I would say it's even preferable to leave it in that form, even if there are more factors. You don't have to write that out. But of course, if you want to multiply that out, if you want to expand that, then that's also fine. But you don't have to do it.
To know if the Taylor polynomial converges or diverges, we would just investigate the limit of the Taylor polynomial, right?
For the Taylor the Taylor polynomial is just a finite polynomial. It always converges. There's no such question here. For the Taylor series, well, it's a series, so you'd have to have a look at the series. That series here, and investigate it with whatever we have for investigating series convergence. Usually you try to apply a test like ratio test or root test, or maybe compare it to some known series, as you have done for series already. That would answer the question, hopefully, whether that thing converges, or for which values of x it converges. That might depend on the value of x. It might not answer the question whether the limit for a given x is actually the same as the function value at that point. That's a different question. If you wanted to answer that, you would have a look at the Taylor remainder that we discussed in the lecture.
What do we need the Taylor series for?
Usually what you want is you want to approximate a function that may be very complex, complicated, and you want to have a good approximation. So basically the Taylor series is hopefully an approximation that is, if it converges to the actual function value, then it's as good as you want it to be. And you can just cut it off at a point where it's good enough. And of course you'd have to find out where it's good enough. Also, it's it's very useful for some, well, how do you want to put that, for analysis of certain functions. It's very useful to have their Taylor series, because it, for example, makes it easier to compare those functions based on their Taylor coefficients. But that's something we didn't really discuss yet, that's right.
Can you explain again for what this is actually useful compared to just computing the tangent at a point of f prime x?
It gives you a better approximation. So for example, let's make a quick sketch. If you have a function that looks like, let's say it looks like that here. So that's a function f, and you want an approximation of that function f. Then let's say we're taking this point here for an approximation. The tangent at that point would be this here. So the tangent is basically the Taylor polynomial of order 1. And if you want a better approximation, then it might be a good idea to use polynomials of higher order for that. So that's here is the best approximation within an affine linear function. But if we would allow quadratic functions, polynomials of degree 2, we could get an approximation that, let's catch up, might look like this. Right, so that might be T2 here at that specific point. And as you can see, that will provide a better approximation, at least as we're close to that point. And hopefully the approximation would get better and better as we increase the degree, right? And work on a more global scale, hopefully. That's the idea. So you want a better approximation than you can get by just the tangent. And of course, you want to work with that approximation, not just at that one point. That's useless. You have the function value there anyway. but you want to work in some neighborhood of that point using that approximation. And the better that is, the larger that neighborhood can hopefully be. So that's why we want Taylor polynomials of higher degrees.
How would you compute the Taylor series?
Well, in general, just compute the Taylor polynomial of a general degree. Again, you'd need some idea of how that derivative here looks like for general k. And then you can just write down the Taylor series. There's not much of a recipe I can give you here. So the interesting point is, how do you get an idea of how that general derivative looks like? And once you have that, it's easy to write down the Taylor series.
Could you explain shortly again in what case we use the remainder?
So if you want, if you have a Taylor series or a Taylor polynomial of a certain function, there's basically two use cases for the remainder. The first one that we also discussed in some examples is if you want to know whether the Taylor series, this one here, actually converges to the function. So the question is, even if we know that the Taylor series of a function might converge, it's not quite sure whether that actually converges to the function value at certain points, x, right? It might converge to something entirely different. And that is a question that you can answer by looking at the remainder. So the remainder is basically the difference of those two for a certain n. That's our remainder. And if that goes to 0, then that would mean that the Taylor series actually converges to f of x. And of course, that property of the remainder going to 0 might depend on x. It might not be true for all x's, but maybe for just a subset of all possible values of x. So that's one application. We want to see if the Taylor polynomial or the Taylor series actually converges to the correct value, the one we want. The other application would be to get a bound on the error. So if we have a function f and we want to approximate that by some Taylor polynomial of bounded degree, like this here, Tn, and we want to be sure that we don't make too much of an error in a certain interval. So we want to keep the error in some interval, usually around x0, so something of the form x0 minus delta, x0 plus delta. We want to keep the error below some threshold. And the question is then, what n do we have to choose to do that? So how to choose n? Well, of course, we don't want to choose n unnecessarily high, because that would mean we have to do a lot of computations. But we don't want to choose it too low either. We want to keep the error below a certain bound. So let's say if we wanted an error below, I don't know, 0.1, for example, and we could use the remainder to hopefully find an n that guarantees that the error is small enough. Well, and that is, of course, the other application of that remainder. I hope that answers the question.
Yeah, I guess. Now, do we have to know how to calculate the maximum difference of a Taylor series and its remainder? So, Taylor relative.
I'm guessing you mean how to compute the remainder and how to bound it, possibly. If that is the question, then yes, you have to know that.
Okay.
By the way, just as a quick remark, there's also a problem that deals specifically with the remainder and finding out about convergence of a Taylor series using the remainder. There's a question about that on sheet 13. I added that, including a solution, of course, by popular demand.
Then there is another, can you show how to compute the general derivative in this case?
To be honest, I have no idea how to do that. So no, I can't show that.
So for the remainder, we need a point x at which we have to compute the remainder, and it is not possible to say whether it converges in general to fx.
Yes, so you need to have a specific point x, and of course, maybe there is a method that shows that the Taylor series converges for every possible choice of x. That would be the optimal case. So maybe the bound is not dependent on x, but maybe it is. It could also be that the Taylor series only converges in some interval around that x0, or only converges to the function in some interval around that x0. That could happen.
Okay, so I think now I can start asking the questions that I have been collecting. So the first one is question regarding Taylor series. Normally it starts at 0 and goes to infinity. But in exercise 12.7, we started at 1. Was it because n equal to 0 is not defined?
Let me have a look at that. So in 12.0, basically what we do is we compute a Taylor series. Yes, the Taylor series. And again, the formula for the Taylor series starts at 0. So you'll have to include that 0 here. So that's, once again, the general formula here, x minus x0 to the power of k. Now, of course, it might be the case that you can find a general expression for that fk that does not include the case of 0. So maybe you can find a general expression for f1, f2, and so on, but maybe not including f0. Then, of course, you can solve that situation by just taking out that first summand. You can rewrite that Taylor series as, well, f0 at x0 over 0 factorial times x minus x0 to the power of 0 plus, and then you start at 1. And that's exactly what's happening in 12.7. So in this case, I just take out that first summand because the general formula for the fk's that I get here does not easily include the case of k equals 0. And instead of twisting that formula to look horribly, I just exclude that first summand and take it out and use it by itself. And if you look at the solution, there's exactly this one term, that 1 plus something, right? So this in 12.7, that is equal to 1. So you get an expression of 1 plus something. That's what's happening there. So you cannot just do without that first summand. You have to include them all, but maybe some summands are more equal than the others, and you have to treat them differently.
Okay, another question related to homework problem 12.7. Could Professor Ritter maybe demonstrate the last step of the problem? So after we had every derivative some values, how can we determine the Taylor series? Because I got some other but similar results than the solution. Thanks in advance.
I don't really see what I could add to the suggested solution here. I mean, once I have the formula for fk, you just put it into the sum, and that's it. And of course, depending on what you did for getting that formula, yours might look different, but it will hopefully produce the same numbers. So if you want to be sure that you got the right formula, maybe just try a few k's, 1, 2, 3, 4, and see if the numbers agree. Then there's at least a good chance that you got the correct formula. If you want to, if you have specific questions about your solution, it's probably best to just bring that to the tutorials and we can have a look at that. It's probably not a good idea to discuss this in front of all participants here.
Okay, then another question is, now we start with sheet 13. For the central exercise for the next week, sheet 13, we only get a video, right? When and where will be this uploaded?
The video has been uploaded already. It's available on Moodle and also on YouTube.
Okay, now what about the next week's? Okay, so central exercises, they're already uploaded, and the quiz is success.
I haven't looked into the quiz, to be honest. I haven't made it before. I will look right after that.
Okay, now general question for the end. Do we only have to consider functions and polynomials in the real domain, not in the complex domain? Because we didn't discuss about complex numbers properly so far.
We didn't discuss complex numbers at all so far. So as far as this exam is concerned, you don't have to know anything about complex numbers. They don't exist up to this point. We will discuss complex numbers in Math 2 next semester. So if you're interested, be sure to join us there.
Okay, then where can I find the code of conduct for signing it?
If you log into TOM Online, you will hopefully have a registration for the exam there. And there's, if you look at that registration, there is a field that's called information. There is a link on that field that works for the TOM exam platform. So just log in there using that link and your immatriculation number. And then you'll be able to download and upload the code of conduct. And just as a remark, please be sure to complete the code of conduct and upload it through TOM exam until February the 10th by midnight. That's the deadline. If you miss that deadline, or if you submit a wrong code of conduct with something missing, then you will not be able to take part in the exam. So please do not forget about the code of conduct.
Okay, so more questions. Can we use another color in the exam? For instance, during taking limits, just like you do with the color orange?
Yes, you feel free to use almost any colors you want, but please don't use red or green, because our correctors will use red and green, and it makes it really hard to differentiate your annotations from the ones of our correctors if you're using the same colors. So any other colors is fine, anything other than red and green.
When will we know whether or not we get a mock exam? And if so, when could it be released?
If you get a mock exam, I'll release it on the following Monday.
Is the certificate of matriculation in the code of conduct mandatory?
Yes, it is.
Okay, now let me quickly change again to the chat because, okay.
Just as an additional remark, maybe if you have any problems with that or anything else on the code of conduct, please don't hesitate to write me a message on the forums or just email me. We find a way.
Okay, now there is one question related to the Taylor series in 12.2. So it says, is my Taylor series correct when I have the sum n equal to 0 and n equal to 2, null? I don't know. I think this one may be better, like bring it to the tutorials because it's impossible to read it out here. Kind of like a formula.
Yeah. It's maybe best to just ask it in the forums or on the tutorials. I can also have a look at the chat later, but it probably doesn't make sense to read it out here.
No. Then is it possible that Professor Ritter shortly explains the reformulations of the functions in 12.3 homework C?
Actually, you should give that a try yourself before I explain it here. And also the suggested solutions are available. So I hope the reformulations are actually explained there. They should be. Yeah. So I suggest you have a look at the suggested solutions if you can't get that done by yourself. And if there's still problems, then you're welcome to ask a more specific question on the forums or in the tutorials.
Okay, then about the mock exam that we already answered, do we have to add the certificate of matricle or is it voluntary? It's mandatory, right?
It's mandatory, yes. Everything on the code of conduct is mandatory. And as I said, if you have any problems with that whatsoever, then please contact me before the submission deadline.
Okay, then it says, what will Math 2 be about?
Math 2 will mainly be about multivariate analysis. So we'll deal with functions that have more than just one variable. That will be in the most part. We'll again talk about continuous functions, differentiation, integration of functions like that, finding out about their properties, how these functions behave, how to graph them. We'll also talk about differential equations, systems of differential equations, and to be able to solve at least a specific kind of systems of differential equations, we'll also need to have a more detailed look at linear algebra once again. And that means we'll talk about what is called eigenvalues and eigenvectors of matrices or linear mappings. And in that context, we'll also encounter complex numbers. So we'll also talk about complex numbers, of course. But mainly it's going to be multivariate analysis.
Okay, some more questions. Could you please outline what documents need to be included in the code of conduct? It is a bit unclear so far.
So the code of conduct basically requires you to do two things. The first is you have to read it carefully. And then in the first problem on that code of conduct, you have to copy a sentence verbatim in your own handwriting and sign that. Basically, you say that you have read, understood, and will follow that code of conduct. Yeah. And the second part of the code of conduct is you upload some identity document. Usually, you'll just use your student card for that. There's 2 pages to that. You upload on the first page. You upload the front page of that identity document, that one containing the photo. On the back side, on the second page, you submit a copy of the back side of that document. The student card is sufficient, but of course you can also use any other form of photo ID if you'd prefer that. But that's it. Yeah, you complete that code of conduct, you fill it out. Please don't forget to copy that sentence verbatim in your own handwriting. Just signing is not sufficient. Also, don't forget to sign. And then you upload that to TUM-Exam using the TUM-Exam submission platform that you're hopefully used to by that point. And again, the deadline is the 10th of February at midnight.
Do we have to include the certificate of matriculation even if we provide a copy of our TUM student card?
If you provide a copy of your TUM student card and that is valid at this point in time, then that's sufficient. You don't have to provide a certificate of immatriculation then.
Do we have to upload the Immatrikulationsbescheinigung or the Studienverlaufsbescheinigung?
No. So the student card is sufficient. It's probably easiest to just use a student card for that ID. You don't have to add another document to that if you have the student card.
Is there any special reader advice for the exam?
Any special advice for? No. Just learn everything.
Yeah.
What I would do is I would go through all the exercise sheets, see if I can solve those by myself. And if you can do that, I will guess you're well prepared for the exam.
It's important to understand because you can do like 1,000 exercises before coming to the exam, believing that you know how to do them, but not understanding them. And then like the 1,001 that appears in the exam is the one that you cannot solve. So it's important to understand concepts.
That's a good point. So it's important to understand what you are doing and not just copy recipes.
And make it clear in the exam that you are understanding and not just write like =2 without really any...
Good point.
Yeah.
So try to make your solution approach clear, transparent to the correctors. These people will have to understand what you were trying to do, even if you make mistakes. So it never hurts to make some notes.
Okay, so now when including our student ID, how much space should it cover? How much space should it?
I don't care, as long as it's readable.
Do we have to participate in Math 2, and who will host the statistic lecture?
Whether you have to participate in Math 2 depends on your choice of focus, I think, but I'm not quite sure what focus that is. So I think for most focus areas, Math 2 is voluntary, but there is 1 or 2 where you have to take it. You either have a look at your study regulations for that, it should be in there. Or if you're unsure about that, please ask your study advisor about that. He or she will know better, much better than I do. What was the second? About statistics, maybe you can answer that.
Yeah, so a statistic lecture, the lecturer will be Professor Rudi Zaxt. He is director of the Chair of Math Finance. And I will be the coordinator for the exercises, so I will be the teaching assistant.
So you'll meet at least one of us next semester.
Yeah.
There's no escaping.
Did we leave out any topics in Math 1 as this semester was a bit shorter than last year?
Let's say we left out a few details. So in some topics, we could have gone a little further, and actually past years did go a little further. I mainly tried to cut down on these details and basically cover all the topics that we needed.
Do we have to fill out the code of conduct if we write the exam in April?
No, the code of conduct that you can submit now is only valid for the February exam. So if you're not planning on attending that, you don't have to do anything right now. For the April exam, if that is going to be online, which we don't know by that point, but if it's going to be online, there'll be a separate code of conduct for that one. So even if you have filled out this February code of conduct and then decided to skip the exam, you'll have to do another code of conduct for the April exam if we're going for the online form once again. Of course, if it's going to be on site, there's no such thing.
If I don't have the student card, what documents should I upload?
Just use some other form of photo ID, like a passport or a driver's license.
So will the exam be similar to the exam sheets? Also from the difficulty?
I would tend to say yes, but of course, remember that most of the exam sheets that I have uploaded were meant for an on-site examination, and that also means a closed book examination. This is going to be open book, so of course, you might perceive it as more difficult or less difficult, whatever works better for you here. I aim to have the same level of difficulty, but of course, there are questions that I just cannot ask in an open book setting anymore.
Do we need to sign on the very top of the first page?
For the code of conduct, it would be nice if you did, but if you have good reasons not to, then it's not strictly necessary.
Where do we have to send the code of conduct to? I can't find any specific link.
You use the TUM exam submission platform. You will have that link on your TUM online exam registration.
While doing derivatives, do we have to explicitly state the way we do the rule we use to compute derivative, or can we just write the first derivative? So I read it again. While doing derivatives, do we have to explicitly state the way we do the rule we use to compute the derivatives, or can we just write the first derivative?
So for easy derivatives, I would say you don't have to state anything as long as you do it correctly, of course. If the function is a little more complex and if the derivative tends to get long, I would make very short notes about the rules that I apply. So mostly because the correctors will then get an idea of what you were trying to do in case you mess up somewhere, right? So if that idea is correct, you might still get a point on something. And if the correctors don't have any idea of what you're trying to do, then that's probably 0 credits.
Is it okay if we only have the expired student card for the code of conduct from last winter semester?
Yes, as far as I'm concerned, that's fine.
Will the form of the Math 2 course be the same as for Math 1?
I would say yes. So at this point, this is just an educated guess, but my guess would be we will not be able to hold a large lecture in the summer, so we'll probably be online again, and that probably also includes the tutorials and the central exercise session. We'd have to think about if we maybe can add some on-site elements to that. So you might not remember. Originally, the Q&A sessions that we are hosting were planned as additional on-site elements, but we had to cancel that on short notice right before the semester start because of the how the pandemic evolved. We can try to do that as on-site elements in summer once again, but I cannot really make a good prediction of how the coronavirus will have spread by then and if it will be possible to do that. But mostly, I'd say the lecture will still be online.
How to indicate that my solution to a problem continues into the next page, pre-printed exam sheet? when at the top of each page is a problem number indicated?
So generally, if you don't complete a problem on its page, or if you don't complete it in the box that is written on the exam sheet, then please just indicate that by like making an arrow at the end and then write something like continued on page so-and-so, so that we have an easier time of finding that. Usually the correctors will only look at the first page or at the box that is meant for the solution of a specific problem, and they will not flip through the whole exam. So if they don't find an indication that it is going to continue somewhere else, they will not search for that. So as long as you make a clear indication that the problem continues somewhere else, then we'll find it.
I think this is related to something we have said before, because it starts. So does this mean we will have to provide more solution approaches and not only the solution?
For the exam, I'm guessing? Probably yes. So for most problems, I'll want the solution approach, the documentation, or justification for your solution, and not just the solution itself, yes. Because I want to know whether you actually know what you're doing or whether you just know how to Google.
I can't find a tab called Information in my TOM Online account to get the link to access to my exam.
Again, if you access your exam registration, that should be available under your exam registrations. If you click on that exam registration, the information should be there. Also, you should have received an email, I think sometime Sunday night when I started that. I made sure to send out notifications using TOM Online, so you should have received an email that contains that link as well.
Is our grade based on other student performance in the exam?
No. There's no grading on a curve.
How would you proceed when computing the Taylor series? Is it best to compute the general derivatives and then plug in the specific values for x?
In most cases, I would do that. I mean, you need an idea of how the general derivative looks like. So in most cases, that will be necessary. And then plug in the value for x, yes. There are other approaches which we haven't discussed a lot that work in specific cases, but in general, I would try that. Find a general formula for the derivative of order k, and then plug in the point.
Will we have checked paper or just these blank boxes?
You'll have blank boxes. Main reason for that is that this checkered paper didn't work well in our trials with the scanning.
Do we have to prove any general formula in the exam?
You may have to prove a general formula in the exam, yes. I'm not excluding that.
Which percentage do we have to reach to pass the exam?
Which percent, sorry?
I think it means like which percentage it has to be correct so that we can pass the exam.
I'll give you, so with the exam, I'll give you a number of points that will be sufficient for passing the exam. That will be somewhere around the 40% mark. But I can't say for sure up to the single credit right now. But around 40% will be sufficient.
Where do I find my certificate of matriculation, and is it mandatory for the code of conduct?
Once again, the certificate of matriculation is not mandatory for the code of conduct. The student card will be sufficient, and you should find it on your TOM Online. There should be a possibility to download that. I can't show you that because I don't have a certificate of matriculation.
Will there be another quiz uploaded for integrations?
I'm not quite sure what the quizmasters are planning, actually. I'll have to talk to them.
Do we need to know every proof Mr. Richard did in the lecture?
You don't have to know it by heart, but you'll have to understand it. And I'd say you'd have to at least be able to apply the methods that I showed you. I mean, for the longer proof where it combines several methods, I wouldn't expect you to be able to reproduce that by heart. But you'll have to understand the methods and maybe be able to apply them to smaller proofs. We just have to apply one or two of those steps.
Is the exam 80 or 90 minutes? I guess long.
90 minutes, yes.
90 minutes.
90 minutes. Plus 15 minutes for the scanning and uploading and printing.
Is there going to be some notification during the exam that the examination time is over and we should start uploading?
No. We don't maintain any contact to you during the examination, so I can't send out notifications. You'll have to care about that yourself. You will find, sorry, if you're logged into this TOEIC exam submission platform, you will find the server time there. So you should get an indication of what time it is for the TOEIC exam server to make sure that you submit your exam on time. Please don't rely on your watch.
Maybe repeat the answer for the question, like which percentage of the exam has to be correct to be able to pass? I mean, there isn't like a specific percentage, and it will be indicated in the exam, right?
It will be indicated in the exam, yes. I expect it will be around 40% of the credits that you'll have to earn in order to pass.
And for the exam, what documents are mandatory if I don't have the student card?
Again, for the code of conduct, please submit some other form of photo ID. For the exam itself, you don't have to have any of these documents attend. That's why we do that beforehand with the code of conduct.
What will happen if the TOEIC exam server will crash during the exam?
Keep fingers crossed that it won't. We deal with that when it happens. Maybe just as a remark, if you didn't notice, there will be a number of emergency contacts on the title page of the exam. It might be a good idea to write these down before you start working on the exam, just in case your computer will crash. Yeah, that will include an email contact. That will also include maybe a Zoom meeting and probably a telephone contact, maybe dial into the Zoom conference. So there will be some way to reach us if there is any kind of emergency. And of course, if the TOEIC exam server crashes, that will qualify as an emergency. That didn't happen so far, so I'm quite confident it will work.
I was about to say that, I mean, for all the exams that I've been involved during the last summer semester, and also the retakes for the previous winter semester that they were also done online, I never encountered any problems. So, I mean, I think the system is pretty reliable.
I would say so, yes. I mean, that's about the same question as asking what happens if an earthquake hits my on-site examination. Well, that could happen in theory. We all hope it won't. If something like that happens, we'll have to deal with it when it happens.
Yeah. Okay, when can we download the blank sheets for the exam beforehand? I don't have a printer.
You can already download the blank sheets for the exam. They're on Moodle. They're under the examinations tab, and there is a link that leads you to the rules for the online examination, and there's all the downloads.
Can I upload a photo of the code of conduct, or it has to be a scanned version using pen and paper? Scanned through a machine, I mean.
Now you can also, so the preferable way, if you don't have a scanner, the preferable way would be to use a mobile phone with a scanner app, because that usually takes care of the borders, cuts out the page correctly. If that doesn't work for you, you can also upload a number of images, JPEGs, to the TOEIC exam server. It should say you exactly what formats it will accept.
And that's it. There are no more questions, and apparently it doesn't seem like nobody's really asking, writing anything. So.
Wonderful. So then I hope you'll more or less well prepared for the exam. You still have a few days to go, so I'm sure you will be well prepared when the exam happens. If there are any more questions, please just post to the Moodle forums, or of course you're welcome to attend the tutorials this Thursday. It's going to be one last round of tutorials this Thursday, and we'll be happy to answer your questions there. If I don't see you at the tutorials anymore, then I hope I'll see you, or see you at least in a virtual way during the examination. Yeah, good luck for the examination. And for those that don't meet anymore in person or online, I hope I'll see you next semester. Good luck.
Yeah. Thank you. And yeah, good luck from my side as well. And remember to understand concepts. That's the most important thing.
Yes, that's right. And thanks a lot to Leslie for moderating this
my pleasure.
all the chats during this semester.
I guess see you, most of you, in statistics.